All right, welcome everybody. I tried to get up here early enough today to the church so there wouldn't be as much glare coming through the glass, but I don't think it worked out. So welcome back. And we are on our last video for our second to last week of Gen Chem. So we're there. And I'm anticipating next week, the last week of class, to maybe be not quite as much material, but we'll see. And actually it's much different material. It connects to everything we're doing here, but it's much more straightforward, the calculations. But I'm actually pretty happy with the way things are going. So where we are on the week 5 slides, I think that's what I called them. Yeah, chemistry or Chem 122 week 5 online slides. We're on the very last topic for acids and bases. And actually, this connects to something that you've done before. And these are called acid-base titrations. Now, there's a picture on the slides of an apparatus where you add the titrants to the analyte, and you put an indicator in there, which is what changes the color at the equivalence point. There's a lot of vocabulary here. So you might want to go back and look at titrations. I think it's section 4.5. So the equivalence point is where you add just the right number of moles of titrant, what you know, to the analyte, which you don't know, and it changes color. That's called the equivalence point stoichiometrically. In the lab, we call that the end point, where it changes color from clear to pink, from blue to green, whatever. And also, you're going to do a simulated lab, if you will, for your last one in Chem 126. And for the chem majors, Dr. Richardson definitely does titration, so I think this is something you're going to see. And there's a million videos out there if you want to see a real-time video of a titration, if you need it. The thing we're going to add on top of it, after I review just some first semester stuff, is measuring the pH during the titration. So not just going to the color change, but what's the pH before the equivalence point, what's the pH at the equivalence point, what's the pH beyond the equivalence point. And there are, the last set of homework problems takes you through that. So let's just jump right in. And this video may be kind of long, but it doesn't have a ton of content. So a lot of it's just me talking and explaining things. Okay, so if you want to get set up, this is letter E, that's fine. And I don't think there's any notes here just yet. It defines what a titration is. Okay, it's already there. I already kind of did that. So you can write down the definition of a titration. So from first semester Gen Chem, depending on when you had the course, I'm just going to slip off my Birkenstocks here so I'm not stumbling around. What we did primarily there was, in first semester Gen Chem, was we used the titration to figure out how much of an unknown there was, how much of an analyte there was, using a titrant, which we also call a standard. So a standard is something that we know the concentration. So we're not going to go through all of that. So the basic idea is this. When you want to do the calculation, you take the molarity of your standard, that's moles per liter, we know that by now, times the volume of your standard that you use to do the titration, so what comes out of the burette in that little picture. And that has to be in liters. Oh, by the way, these can be reversed, because the units cancel. Moles per liter times liters gives you moles. And that's stoichiometry. We always want to find moles of our starting material. Then you go to your balanced chemical equation, and sometimes there's more than one. When we did a redox titration, if you had first semester Gen Chem, we had to use 2 mole ratios here because we had 2 balanced equations. So sometimes you have to use more than one. I'm just going to use one example, or example 1 here. Then it depends on how you want your units to be for your final answer for amount of unknown. Well, that can mean different things. That can mean molarity, that could mean mass, that could be mass percent, it could be mole fraction, it could be anything, any one of those things. We're just going to consider a couple of things here. So if your goal is to get the molarity of your unknown, if that's your goal, to get the molarity of your unknown, the monk, then you would simply divide by the volume of the unknown in liters. So typically in that little picture there, you measure some fixed volume and put it in the Erlenmeyer flask. So you know what that volume is. It's not a calculation, it's just something you measure out. Oh, a little fun fact, if you leave this in milliliters, because that's typically what we do in lab, and leave this in milliliters, typically what we do in lab, then you don't have to do the conversion twice. It's not a difficult thing to do. So that's what you would do there, but if you wanted to do something else, like determine the mass of the unknown, well, that's pretty straightforward. To go from moles to mass, you know what you do there. You would multiply by the molar mass of whatever it is you're analyzing, and typically you know what that is. So if you're analyzing, I don't know, calcium carbonate, well, you just look up calcium carbonate on the periodic table, CaCO3, and add all that up. And if it's a hydrate, make sure you add in the hydrate and go from there. So that's kind of a review of Gen Chem stuff. I'm not sure I'm going to ask you any questions like that on the final, but that's a good standard thing you want, no pun intended, that you want to be able to do after taking a year of chemistry, is understand how to do that. And I'm just going to whip through these two examples that are on here, because it's kind of taking away from where we're trying to head out. So the first one is, okay, calculating the molarity of HCl, and the second one is calculating the mass percent, so mass of the analyte divided by the mass of the sample. Okay, that's fine. I'm just going to kind of quickly write these out just so you can see them. And I'm not making a big deal out of these. So you don't have a balanced chemical equation here. I kind of like doing this side-by-side thing. So you need this actually introduces something. So the first one, we're taking sodium hydroxide. All this stuff's aqueous. I'm not going to write AQ, and waste time with that. So we've done this one so many times, and this is not an equilibrium. And I'm going to use this example in the next section. So it's a strong base, strong acid. So this is a strong acid-base titration, or base acid. So there's no equilibrium here, so I'm not going to do the double-headed arrow. And it's acid-base, so it's neutralization. And I said I wasn't going to put those. So it's, all right, you've seen that before. It's just neutralizing the solution and making it salt. So at the equivalence point, the pH here should be 7, because we've completely neutralized the acid and the base, and it's strong acid, strong base. The other one, which I think you need, I don't think I gave to you, is what are we analyzing here? What is the mass percent of sodium carbonate? And we're still titrating with hydrochloric acid. The only reason I did this one, so here's sodium carbonate, and you're reacting with hydrochloric acid. And it's also not an equilibrium. Well, we'll get to that later. Now I bring this one up because I think this is what you're going to do for your case study in the lab. So this is actually an acid, obviously a strong acid, and this actually is dibasic. Carbonate has 2 Kb values, so I'm just going to give you a heads up for the lab, for those of you that are in the 126 lab. This is the chemical equation you're going to use, and we just have to balance it. And carbon dioxide is given off as a gas, so I really should put that G over there. But all we really care about here is the stoichiometry in this problem. So, all right, let's just blast through these. These are not typically all that difficult to do. And what did I do here? I gave you things in milliliters. Let's be a little sophisticated here. Milli means 10 to the minus third. So we have, and I'm going to do the volume first. I think a lot of you like to put volume first because it only has 1 unit rather than a compound unit, moles per liter. So 9.55 times 10 to the minus third liters of NaOH. That's our standard, isn't it? Yeah, we know the molarity of the NaOH. Times 0.1032 moles of NaOH. That's really small, I'm sorry. That's the molarity of the NaOH per liter. It's a 1-to-1 ratio. And what are we trying to calculate? The molarity. And how much did I put in the Erlenmeyer flask? 10 milliliters. That's 10 times 10 to the minus third liters, or 1.000, got to carry all those sig figs, times 10 to the minus 2 liters. So if you can't read that, just set it all up like this. this, and you should get an answer of 0.0986 molar HCl. So we did that calculation, my goodness, in the first month or so of first semester Gen Chem. So just keep that in mind what we're doing here. Excellent. And some of this stuff's going to come back. And, okay, so mass percent one. Okay, mass percent. We already know this. It's the mass of the analyte. So the mass of the sodium carbonate divided by the mass of the sample times 100. Now here I didn't give you a mass of the sample, I gave you a volume. And we're just assuming that it's the same as water. So the mass of the sample, we just have to use a simple density calculation. It's a 2 milliliter sample, and we're assuming it's mostly water. So a milliliter of water, which I gave you, I think, in the problem, was 0.9986 grams. Well, actually, with three significant figures, this turns out to be 2.00 grams. So it doesn't even change the value from 2 mils to 2 grams because of sig figs. But convince yourself of that. These are basic things we don't want to forget. Okay, so here let's just whip through the calculation. And I just give you some different numbers, I think. 4.21 mils of, okay, now we're using acid to do the titration rather than base. So, but it doesn't matter. So 4.21 times 10 to the minus third liters. Let's make this go a little faster. We're doing HCl first, and we're going to Na2CO3. So I'm going to be a little sloppy here. Times the molarity, 0.0185 moles of HCl per liter. It's a 2-to-1 ratio. The 2 goes at the bottom. And we're trying to get to this. You can convince yourself that the molar mass is 105.99. There's no hydrates or anything. So it's 2 sodiums, carbon, 3 oxygens. 105.99 grams per 1 mole. And well, again, I'm being sloppy. Now that'll give us grams, so that'll go up here. Okay. And this is 4.13 times 10 to the minus third grams of sodium carbonate. And I'm going to let you finish this off. So you would take the grams of sodium the grams of sodium carbonate, put it here, the mass of your sample, and put it here, and you should come up with a really small answer, 0.206%. So I'll let you finish that one off. It's a pretty easy problem, I think, compared to what we've done so far. And that's really first semester stuff. Okay, I'm going to keep this video rolling, not going to use this as an introduction or anything like that. But those are titrations that we did in first semester where we only considered one point, the equivalence point. Why would we want to do anything else? Well, there's a few things we can learn. So what I'd like you to do is we'll move to the next slide. While I'm erasing this stuff, don't worry about it. You can set up your notes, number 2, acid-base titrations, and we're going to consider a strong, we already did that, didn't we? Well, actually, we're going to continue that. So case 1 is this. And then we'll go to another one there. So what I really want you to pay attention to while I'm erasing up here is the shape of those 2 titration curves. The first one is a strong acid-base titration. The second one is a weak acid being titrated with a strong base. Notice the differences in the shapes of those curves, the differences in the equivalence points between a strong acid, where the equivalence point, the pH is 7. But it's not 7 in the case of a weak acid. So just notice the differences there side by side. I'm pretty sure I just pulled that from your book. So take a look there, set up your notes. Yeah, okay. Oh, I don't think I put a number 1 here. What was number 1? Oh, yeah, E1 was just the definition. Okay. So let me get it set up here, take a little bit of time. And maybe I can just do the calculations here and you can review the different positions on the pH curves. I'll see how that goes. So we are doing now number 2, acid-base titration. Well, we already talked about that. And maybe I will try to do these side by side. So case 1, what did I call it on here? Strong acid, strong base. Case 2, weak acid, and we'll keep a strong base. Actually, for reasons we probably aren't going to go into here, you would never titrate a weak acid with a weak, unless you're trying to look at some kind of chemistry between the two. You would always keep one of them strong. So what we're showing you here is we're going to keep the base strong and titrate weak acids. In lab, quote, lab, you're doing the exact opposite. You're going to use a strong acid to titrate a weak base. And it's actually dibasic. So the pH curves, I'm giving you a little heads up on your lab, are actually going to be the inverse of those pH titration curves. And they're going to have 2 equivalence points. I just gave away some stuff for the lab. Okay. So what we do with these calculations is we consider 3 points: before the equivalence point, at the equivalence point, and beyond the equivalence point. And that's what we're doing in both cases here. And what are we doing? We're calculating pH. Fine. So what you'll notice, and let's see, maybe I'll try to be a little fancy here, is a titration curve. Maybe I'll put that one here, and this one here. Again, you can find videos, and it's really unfortunate we're missing lab because this would have been one of the really nice things, is you take a pH meter. It's an electrode, it just looks like a little plastic tube. It's kind of interesting, you can see this online. And you put it in the solution, and instead of just going to the color change, you add, in this case, strong base, and you monitor the pH. So if this is a strong acid, strong base, so you're putting acid in the Erlenmeyer flask, the pH starts kind of low. You keep adding, the color starts to change a little bit, and then boom, it shoots way up, and then it levels off. This is an exaggeration. It's not exactly the same as on here. And I'm just doing this qualitatively. I'm not putting any numbers here. And that's really terrible. It's not quite that flat, but it makes the point. Something that's a weak acid, and we're going to assume, by the way, that we're using the same molarities. So if it's a weak acid, it's going to start up. It's going to start higher on the pH scale, because remember, strong acids, we don't do any equilibrium or ice calculations or anything like that. So the pH is just the molarity of the acid. Over here, what you see is you get a much more gradual change, and then it'll shoot up, and then it'll kind of be a little bit more of a gradual change. And that's an exaggeration, but that's the qualitative difference in the two shapes. The book has a much more precise one, and it also gives you tables of data where you can practice the calculations I'm about to show you. So if you don't quite get them, you can go there and repeat them, and they give you all the answers, and you can do those as much as you want. All right. So in the first example, we're titrating 25 milliliters, fine, of acid. So the pH for this first one is 0.1. So you do the minus log of that. The pH here is going to start out at 1, by the way. Just throwing that in there. guess I already did that one. Calculate the pH after the following, noting, okay, for a strong acid. Well, I already did A, I guess. All right. So A, we've added no sodium hydroxide. Oh, I think this is exactly the one from the book. I just should have looked at my notes. Yeah, this is exactly the same thing as your book. All right, I'm going to streamline this because I think I'm making this way too complicated. And yeah, for this one, I'm just going to kind of make the point here. So zero, so the pH here is going to be minus log 0.100 molar. So before we even start, we know the pH should be 1. Okay, that's maybe not that difficult. Let's see, what does the next one say? 22 milliliters of NaOH. Okay, well we know the equivalence point should be at 25 mils. We know that. Why? Because the molarities are the same. We're not doing an unknown here. We know what the molarities are. They're both 0.1. We're using 25 mils of acid, so it should take 25 mils of base. So that's okay, it's 1-to-1 ratio, it's not too tough. So the problem here is if we are before the equivalence point with 22 mils, I'm going to do something I think I only did one other time. So this is before the equivalence point. And we know what the pH is going to be after the equivalence point, or after the equivalence point, by the way. It's going to be 7, so we're not going to do that calculation. We do something I think we did once before. We do something called an if table. And this is something you are going to do in the lab, so this might be helpful. So an if table is just initial final. It's not an ice table. I think I did one of these before. My memory's a little shaky on this one. And here we use moles. So we can do stoichiometry directly rather than molarity. I think you'll see what I mean. It's really not that tough. So remember what we're doing here. We're taking hydrochloric acid and sodium hydroxide, and we're producing water and sodium chloride. Okay, so what's the point? What are we doing here? So the initial number of moles of hydrochloric acid, that's how many moles are in the sample. It's 25 mils, 25 times 10 to the minus third liters, or 2.500 times 10 to the minus 2 liters, times 0.1 molarity. So if you do that math, you have 2.500, I think that's the right number of sig figs, times 10 to the minus third moles of HCl. Okay, that's how many moles are in the original sample. Molarity times volume, don't overthink that. Well, we've added 22 mils of sodium hydroxide, so let's just assume we can, this is all kind of a fabrication. 22 mils of 0.10 is going to be 2.200 times 10 to the minus third moles. Remember how we do this, it's 0, 0, and I'm going to make this really simple. This is a limiting reactant here because it's before the equivalence point. All that's going to be gone. All you have to do is subtract these two. Subtract these two, because if all of that's gone, the number of moles of HCl left is going to be this minus this, and you can double check. It's 3.00. Oh, I guess, yeah. Times 10 to the minus fourth mole. So we lost almost all the moles of HCl. We're just subtracting these two, don't overthink it. And over here, we get 2.00 times 10 to the minus third moles of water, and 2.00 times 10 to the minus third moles of HCl. Okay. But remember, when we do pH calculations, we want to know not the moles, but the molarity. Okay. Well, what's the molarity of the HCl at this point? Well, molarity is moles per liter. So it's 3 moles or 3 times 10 to the minus 4 moles of HCl. The trick is, what is our volume now? Our volume now is 22 mils plus 25 mils. So that's, what, 47 milliliters total volume? You have to keep track of the volume of the titration. Keep adding more volume here to the 25 mils originally. That's all. You just keep in mind where you are in the experiment. You just keep adding the volume. So you end up getting 4.700 times 10 to the minus 2 liters. This is really better in the lab because this is 47 mils total. 22 plus, well, 25. And you end up getting a concentration of 6.38 times 10 to the minus 3rd molar. HCl, it's a strong acid, so we calculate the pH based on this. So pH is going to be minus log of that, and I think you can handle that. At this point, you get a pH equal 2.19. Fine, that's before the equivalence point. The next one, I'm going to need some time to erase here, is, and again, I think this is just really a setup for where we're headed. The next one is after the equivalence point, 30 mils of NaOH. So the total volume now is going to be 25 plus 30. The total volume is going to be 55 milliliters, so just keep that in mind for later. Okay, I'm going to erase this and do C right here so I don't have to rewrite all this stuff. So just take a minute and go ahead and work on it if you want to. The only thing that's going to be different is all the HCl is going to be gone and there's going to be NaOH left over. So we're going to calculate a POH and then calculate a pH. It's really not that different. Okay, so I want to erase this, and I want to erase that actually. Okay, so I'm just going to set this up. And there's not going to be any HCl left, it's going to all be gone. We're still doing this. And this is letter C, 30 mils of NaOH have been added, and this is now after the equivalence point. Okay, well, you see where this is going to go, I imagine. Our initial moles of HCl is always, it's just what's ever in the flask to start the experiment. The NaOH now is, it's just 30 mils now. Okay, well, it's 1 to 1, so this is going to be gone. Subtract these two. That's the same, that's just bumped up, so that's now excess. This is now limiting, so you have 5, so the thing we really care about, and all the HCl turns into water and HCl, or NaCl, excuse me. So all we really care about here, well, we can't base the pH calculation on nothing for HCl, so we have to base the pH calculation based on the hydroxide now, because that's what's left. Well, that's fine. So our concentration of OH minus, let's be a little sophisticated here. Sodium is a +1 ion. It has no acid-base properties. It is total spectator. This is a strong acid, so we can just jump right to this. It is 5.000 times 10 to the minus 4 moles of OH minus divided by the total volume. 5.500 times 10 to the minus 3rd liters, also known as 25 milliliters. And you get 9.09 times 10 to the minus 3rd molar OH minus, which turns out to be a POH of 2.04. which means a pH, now it should be basic at this point because all the acid is gone, 11.96. So we're way up here somewhere. So the pH, boom, shoots way up. So the pH is pretty low to start. Right before the equivalence point, the pH might come up a little bit to whatever it was, 2 point something or other. But after the equivalence point, all we're doing is dumping in OH minus. That's all we're doing. So the pH just goes higher and higher and higher. Okay, that is strong acid, strong base, and it's really not that much of an extension off of what you did in first semester Gen Chem. We're just putting a pH probe in there and doing stoichiometry calculations. Okay, let's switch over to weak acid, strong base. Again, in lab, you're doing the exact opposite. Okay, I'm going to leave that there, I guess, for now until I need the space. A couple of vocabulary terms that I can give you. The last video talked about buffers. So a buffer is where the pH doesn't change very much. In titration curves, there's parts of the pH curve where the pH doesn't change much. That's called a buffer region or a buffering region. So the pH doesn't change a whole lot. There's some buffering capacity is sometimes the phrase that's used. Then the equivalence point is somewhere in the middle of this steep curve. In calculus, if you've had calculus, this is called the inflection point, where it goes from concave one side to concave this. I guess this is concave up, concave down. That's called the inflection point. That's the equivalence point, and in lab we want that also to be the end point. I'm not labeling all that on here. That's where the color change should occur, right here. And then you go beyond the equivalence point, and you get another buffer region. You're going to see this more in lab, so this is just kind of a little bit of help. So what we want to do, this is before the equivalence point, this is at the equivalence point, this is beyond the equivalence point. So it's acidic here, it's, well, somewhat acidic here, and it's basic here. So we want to do the same three calculations, but we have to take into account some equilibrium considerations. Okay, so the way we have to do this, and I think I'm going to need more space, is we have to do two things. We have to do an if table. Then we do an ice table. So it's if, ice, and it works out pretty well. Okay, yeah, I'm going to need this space. Because I think it's good to see all three calculations together, and maybe I'll try to set it up so we do all three together. I can streamline this a little bit. So now I'm switching slides. Okay, all of the concentrations are the same. We're still using 0.1 NaOH. We're using 0.1, in this case it's acetic acid. We always use acetic acid because it just makes sense. And we know the Ka of acetic acid, my goodness, is 1.8 times 10 to the minus 5. Okay, okay, I think we're set for this. Let's try, you know what, I'm going to try to do these side by side. So we're going to do A, we're doing A, B, and C. Maybe this is going to get too fancy. So we're doing 20 mils of NaOH, so that's before the equivalence point. We're doing 25 milliliters of NaOH, so we're at the equivalence point. And then we're doing, maybe this is going to get a little complicated, but we'll try it. And we're doing 30 mils of NaOH. Oh, again, incidentally, I'm just reiterating this. The book has a whole table of volumes and pHs. You can practice this like crazy, and they give you all the answers. Just make sure you can see that. I'm going to check to see if this is recording okay before we get into that, so you can see everything. Okay, so before, at, and beyond the equivalence point. Fine, I think you can read that okay. My marker is starting to die a little bit. And incidentally, we are doing the exact same chemical equation, and I want to simplify this a little bit. I want to strip out all those spectator ions. In this case, it's only sodium. So here's what we're going to do. We're going to do an if table, an ice table, and a pH calculation. So if ice pH, if ice pH, if ice POH, okay, and go from there. So I think once we set up the math, it's going to be pretty straightforward. So I'm kind of glad we're doing it this way. And the chemical equation is always the same. So it's always acetic acid, so HC2H3O2, just to reiterate, this monoprotic. And we're titrating with sodium hydroxide. It's just OH minus. And we're producing water and acetate. So if ice, and that's, I took up too much space. Okay, so I think that's right. Yeah, it actually doesn't really matter that much. So it's acetic acid being titrated with this, and we're producing. Okay, and this is, you could go through the Bronsted-Lowry definitions here. So we're going to do an if table with moles, and then we're going to do an ice table with molarity. And we're going to do that for each of these. So I may have to spread that one out a little bit. That's okay. So if ice, if you just want to take a look at this. All right, so I'm going to streamline this. So if is easy. We just take the volume of whatever it is we're dealing with and multiply by its corresponding molarity. So for the first one, we're using 25 mils again. Well, that's pretty easy. So it's 2.500 times 10 to the minus third. And it's 20 mils of this, so it's 2.000 times 10 to the minus third, 0, 0, okay, that's 0, it's the limiting reactant. We subtract these two, 5.000 times 10 to the minus fourth. See why we did that before? This is 2.000 times 10 to the minus third. This is 2.000 times 10 to the minus third. We really don't care about those. Fine. Now we turn those into molarities. Well, the initial molarity here is, oh, I forgot one thing. Yeah, I forgot something. An if table is not an equilibrium. An ice table is an equilibrium. I forgot to mention this. This is kind of important. So before the equivalence point, we have acetic acid around. Before the equivalence point. So our only acid-base species in an equilibrium is acetic acid. So what's the equilibrium that we have to look at? Well, it's the acetic acid equilibrium before the equivalence point. So the equivalence point for our ice analysis, yeah, that was kind of a dumb thing for me to overlook. The equilibrium is actually an acid equilibrium. Over here, it's going to be a base equilibrium. Just keep that in mind. So C2, H3O2, it's still an acid, so we have to show acetic acid as an equilibrium. Goes to H3O plus C2H3O2 minus. So again, to reiterate, before the equivalence point, it's an acidic equilibrium. Actually, at the equivalence point, it will be too. So this is how we base our ice table. Okay, and water we always ignore. You can see where we're going to be home free now. And, okay, so what are we dealing with? Well, we don't know, we actually know two of these things, don't we? The initial concentration of acetic acid is going to be this moles divided by the total volume. So I'm going to let you figure this out. 20 mils added of NaOH plus 25 mils is 45 milliliters, so 4.5 times 10 to the minus 2 liters. So we have to convert this into a molarity, but we have to convert this into a molarity as well, because we generated some acetate ion. So you take this moles and turn them into molarities, and you should get 0.011. Moles divided by volume, 20 plus 25 is 45. Again, double check all that. And normally with ice tables, with some exceptions, buffers we did this, we just start here and push everything that way. But in this case, we have stuff on both sides. It's not a big deal. 5% rule will still work. And we have none of this to begin with. So the equilibrium, Le Chatelier's principle, has to go this direction. Yeah, my little dream of putting all these side by side isn't going to work. So, sorry about that. Now I think we're kind of home free. We're going to do the 5% rule thing. I'm going to jump right to it. We know our Ka is 1.8 times 10 to the minus 5. We know that, and we're going to invoke the 5% rule automatically. So we're going to ignore as negligible this x and this x. We can't ignore this x, of course, because that would make the whole thing 0 and the whole thing pointless. So we're going to say that Ka is approximately x, these two things combined, times 0.044 molarity divided by 0.011 molarity. Okay, solve for x, and I came up with x equals 4.5 times 10 to the minus 6th, and that's a molarity. Now what is x? Well, x is the H3O plus, so we just take the minus log of that, and the pH should be 5.35. And the 5% rule does work, but you check it yourself. How would you check it? Well, you would take x divided by the smallest initial concentration times 100. It's way, way less than 5%, so we're good to go. But I'm going to let you check that. So that's how you do it. You do an if table. You figure out, so the basic procedure is this. If table, what equilibrium do you have? Is it acidic or is it basic? And then set up an ice table and go from there. So this is how you do before the equivalence point, and let's finish off the last two because the video is getting super long. And if you know what you're doing, if this makes sense, then just ignore this, as long as you can do the problems. All right, so again, that was dumb to try to do all of this. I tried, it didn't work. So this is B, 25 milliliters. So this is at the equivalence point. Maybe this will be the same equilibrium, so I'm just going to leave all that for now. And what didn't I have to erase? Well, I didn't have to erase. Well, let's just leave that and see if it works. Okay, so this is at the equivalence point. I'm just going to erase all these, I don't know what those are. Okay, so we still have the same initial moles. Well, that's fun. Well, aren't they the same? The moles of acid and the moles of base are exactly the same. So, what was the equivalence point, right? So they're both gone. There is no limiting reactant, they're both limiting. It's a perfect ratio. So all we do is take the moles of acid and base and convert those into water. Well, that's fun. What does this tell us about the equilibrium? This is the key. This is actually a really good problem. And this will tie into some of the stuff you're doing in the lab. This shows that you really know what you're doing. So we've taken the acid and the base, we've combined them in a perfect equivalence point, and we've converted everything into water and acetate ion. This equilibrium does not work anymore because we don't have any acid. What do we have? We have its conjugate base. This ties in so many concepts, which is why we do titrations. This is the conjugate base of acetic acid. If this has a Ka, this has a Kb, which you can solve that problem. Ka times Kb equals Kw. So you could get a Kb for this, but what's the equilibrium? Well, it's not an acid equilibrium anymore. It's a basic equilibrium. So if it's a base, then we have to look at this acting as a base. Well, how do you write that? Well, you write it reacting with water to regenerate the acid. So in this case, this is the base. This would be the conjugate acid. And it's base, so we're producing OH minus. This is the equilibrium we now have to consider because the chemistry is different. This is what we have. Maybe I've said that too many times. Okay, so we've added, so now we don't care about the water. These are 0 to start out. So what's the molarity? Now we're going for molarity. What's the molarity of the acetate? Well, here's the moles. The total volume is 50 milliliters, and you should get 0.050. Okay. I think we're home free now. It takes a lot of work to get here, but now we're home free. And we're going to calculate pOH. And we can't use Ka, we have to use Kb. I'm going to streamline some of this stuff because I think you can do it. And we've done this one before. So calculate a Kb, and you're going to get a Kb of about 5.56 times 10 to the minus 10. Again, that's a Kb from the Ka, do that yourself. And that will give us immediately, that 5% rule better work. If it worked for 10 to the minus 5 before, it better work for 10 to the minus 10 now. And it's going to be approximately equal to x times x. We don't have anything on both sides like before. So this is x squared over 0.050 molarity. Okay. And I come up with an x, which in this case equals the hydroxide, we want that, of 5.27 times 10 to the minus 6 molarity. 5.27 times 10 to the minus 6. That gives us a pOH of 5.3 and a pH, which is ultimately what we're after, of 8.72. Wow, okay, that's a lot of math. It's important to recognize the fact that we have a basic equilibrium to consider here, and that the equivalence point for a weak acid being titrated with a strong base, the equivalence point is not 7. It's not a perfectly neutral solution like strong acid, strong base. It's actually higher. So the equivalence point for this one, if you just did this graph, would be 8.72. Not 7. It's not completely neutral, but that's the difference here. Okay, and the last one, beyond the equivalence point, is actually very, very easy. Whew. So, beyond the equivalence point, all we're doing is dumping in more OH minus. All we want to do is figure out how much excess OH minus have we dumped in. Calculate a molarity and a pH. I don't even think it involves. No, it doesn't involve an ice table. Yeah, because we're going to assume that OH minus is so much stronger and will dominate. This is just a minor point. Ah, shoot. Okay, I have to rewrite all of that. So we are beyond the equivalence point now. I'm just going to whip through this because I think it's pretty straightforward. So we're at letter C, 30 milliliters. We've exceeded the equivalence point. Okay, if table HC2H3O2 plus OH minus produces water and so that's just the titration equation, not an equilibrium. So it's just chemistry. So we do if 2.50 10 to the minus third moles there. Now we've got 3.000 times 10 to the minus third moles here, so we've exceeded it. That's gone. And we have okay, we're going to assume something here. That the presence of a strong base, OH minus, NaOH, which is a strong base, dominates the pH. That we've now gone, so there's 25 mils, now we're up here and say 30 mils. That the pH is pretty much dominated up here by all that excess OH minus. So we're just going to go right from that to calculate the molarity again based on this. So the molarity again, it's moles per liter. Keep a running tab of the total volume. 30 mils plus 25 mils is 55 mils. So 5.50 times 10 to the minus 2 liters. You can do that yourself. You should come up with a molarity of 9.09 times 10 to the minus third molar. Again, just moles divided by total volume. pOH equals 2.04. pH equals 11.96. Whoops. So we've completely dominated the scene with OH minus, and we really don't have an equilibrium anymore. We've gone through this, and all we have left is OH minus. We just keep dumping it in, and the pH gradually gets higher. And I think that's it, folks. That was a super long video for titrations. But make sure that you understand the difference between a strong acid, strong base, and a weak acid, strong base titration. Complement that in the lab with the exact opposite, with a couple of twists, and we are good to go. And that is the end of acid-base chemistry, officially. Nice work.